Hello and welcome to the AICE Chemistry lecture series. Today we're going to be taking a look at chapter 6 section 3, which is going to focus on measuring enthalpy changes. We discussed enthalpy changes a lot at this point, and we discussed what the numbers mean, but how do we actually get those numbers? So when we talk about the enthalpy change of a neutralization reaction, for example, how do we get that number? Where does that number come from? So the main way in which we get enthalpy numbers in chemistry, in practical terms, is through a technique called calorimetry. Now, there are various types of calorimetry, but they all, in essence, do the same thing, which is measuring the amount of heat given off or absorbed by a reaction. The most simple type of calorimetry, which we're going to talk about first, and the one that we use for the practical, is called styrofoam cup calorimetry, or just coffee cup calorimetry, or just sometimes just referred to as calorimetry. In this type of calorimetry, what we're going to do is we're going to create an insulated system. Now, we talked about an isolated system earlier in section 1, which is a system where both mass cannot enter or escape a reaction, and heat cannot enter or escape a reaction. So obviously a perfectly insulated system is not realistic, it's not going to exist, but we do our best in isolating the system as much as possible. In calorimetry, what we're going to use is we're going to do an isolation of the chemical solution so that the heat has nowhere to escape but to the solvent. So this is what we call a coffee cup calorimeter. We're going to put essentially what is a coffee cup or a styrofoam cup. Notice it says plastic here because styrofoam is a type of plastic. And so we have the styrofoam cup, and that is going to be placed in either another styrofoam cup or a beaker or something to hold it. Into this, we're going to put a thermometer with some kind of cap or top to our styrofoam cup. And in the cup, we're going to put our reaction mixture, which is simply just the chemicals that are reacting along with whatever solvent they might be in. So the concept of a styrofoam cup calorimeter or a coffee cup calorimeter is very simple. We do a reaction that happens in this coffee cup or in this styrofoam cup. So we have a solution with the individual reactants that are reacting with each other. And when those reactants react to each other, they will either give off heat or absorb heat. For the idea here, we're going to say that they give off heat. That heat has nowhere to go due to the coffee cup being an insulator. So when that heat is trying to escape the coffee cup, because styrofoam is such a good insulator, it has nowhere to go but the surrounding solvent, in most cases the water that is floating in. Remember from our conversation in section 1, the solvent, the water in this case, is not part of the system, it's part of the surroundings. So let's say this pink dots where the reaction between sodium hydroxide, aqueous, and hydrochloric acid, HCl aqueous, to create water and sodium chloride. Because the reactants here are sodium hydroxide and hydrochloric acid, those pink dots, this reaction being exothermic, delta H being negative, means that this reaction is giving off heat. Well, that heat has nowhere to go because of the styrofoam cup. The only place that heat can go is the only part of the surroundings that we have within the cup, which is the aqueous water. So that aqueous, which is water, is going to be part of the surroundings. Why? Because it is not participating in the reaction itself. The reactions between sodium hydroxide and HCl. The water, the solvent, is very part of the surroundings. And so when the heat is given off by this reaction, because a coffee cup does not let it escape into the air around it, the only quote-unquote surroundings that it can go into is that water. So aqueous, remember, aqueous just means a lot of water. And so what happens? We, through this thermometer that we have put in here, can measure the temperature of that water. And so we can directly measure the amount of temperature that the water either goes up or down by, and therefore say a few things about the reaction. If the temperature of the water increases, so let's put that here, if the temperature increases, that means the reaction is exothermic. Why? Because if the temperature of the water goes up, that means that it's absorbing the energy that the reaction is giving off. If the temperature goes down, on the other hand, then we have an endothermic reaction. Since the water is part of the surroundings, if the temperature goes down, that's because the reaction or the reactant particles, the sodium hydroxide and the HCl, are absorbing energy from the water. So in calorimetry, what we're measuring, and this is a very, very, very important concept, what we're measuring is not the temperature change of the system. We cannot do that. We can't measure the temperature change for the individual reactant particles. We're measuring the temperature change of the surroundings, not the system. So the temperature change is of the surroundings, the solvent in this case, and that can give us an idea of whether the reaction or the system, let me fix that, the system is endothermic or exothermic, the reaction. Because if the reaction is endothermic, that means it's absorbing heat. Well, it's going to absorb that heat from the surroundings, making its temperature go down. If the reaction is exothermic, if the system is exothermic, it gives off heat, and that heat is picked up by the surroundings, and the temperature goes up. So, the styrofoam cup is an excellent insulator. This is very important here because we will talk later about the errors that come into this kind of practical lab. And some of the error will be from heat loss or heat gain from outside of the styrofoam cup. But the reason we use styrofoam is because it's a perfect, not perfect, but a really excellent insulator, and it's very cheap. It keeps the heat trapped inside of the styrofoam cup, and so we can directly measure the amount of heat either absorbed or given off by measuring the temperature of that solvent, of in most cases that water. Now, calorimetry only gives us the amount of temperature change. How do we convert that to energy? We convert that to energy through a property of water, or property of the solvent, which is called specific heat capacity, which we symbolize by the letter C. Specific heat capacity of a substance allows us to convert temperature change to heat energy, to kilojoules or joules. And that's because when we look at temperature change of a substance, specific heat capacity is the relationship between temperature and heat. Specific heat capacity is defined as the energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. Remember, because we are talking about a change, Celsius and Kelvin mean the same thing. So it's the energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. So imagine I'm talking about the specific heat of water. If I have a drop of water that weighs 1 gram exactly, the specific heat would refer to the amount of energy in joules that it will require for this 1 gram of water to go from, let's say, 0 degrees Celsius to 1 degree Celsius, or from 273 Kelvin to 274 Kelvin. This is why we say that the change is the same. Even though Kelvin and Celsius are not equal to each other, 0 degrees Celsius is not 0 Kelvin, the changes, delta C, the change in Celsius, is equal to the change in Kelvin. Because if I go from 0 degrees Celsius to 1 degree Celsius, I'm going to from 273 Kelvin to 274 Kelvin. Both of them are a change of 1. Delta is equal to 1 in both cases. So a change in Kelvin is equal to a change in Celsius, even though Celsius are not equal to Kelvin. So that's what specific heat capacity is. The amount of energy that it will take to grab 1 gram of that substance, in this case we're looking at water, and change its temperature by 1 degrees. And that doesn't have to be from 0 to 1. It could be from 1 to 2, 2 to 3, 3 to 4. It will always take the same amount of energy. Now, when we look at specific heat capacity, different chemicals have different specific heat capacities. For water, which is the solvent that we normally work with when it comes to calorimetry and when it comes to just chemistry in general in this class, the specific heat capacity of water is 4.18 joules per gram Kelvin, or per gram Celsius. What does that mean? It means it takes 4.18 joules of energy to raise 1 grams of water's temperature by 1 degree Celsius. That's why it's joules per gram Celsius, or joules per gram Kelvin. Because again, Celsius, Kelvin mean the same thing. Because the amount of energy in joules that it takes to raise 1 gram by 1 degree Celsius, or 1 gram by 1 Kelvin. So for water specifically, that's 4.18 joules of energy that it will take to grab 1 gram of water and raise its temperature by 1 degree Celsius. Different chemicals have different specific heats. Metals, for example, have much lower specific heats because it takes a lot less energy to change the temperature of a metal. That's why they get so hot when we put them on top of a fire or out in the sun. Whereas something like styrofoam has an extremely high specific heat because it takes a lot of energy to raise the temperature of styrofoam. So this is the key to calorimetry, for us to convert that temperature that we record into joules. We need the specific heat of this solvent, the surroundings that we're working with. In most cases, it's going to be water, so that specific heat is 4.18. And you should memorize this, although most questions in the AICE exam will give you this number. Sometimes you will see this number as given as 4.2 joules per gram degree Celsius. That's fine. It's just a rounded version of that same specific heat. So, if we have the specific heat of water and we have the temperature change from a calorimetry, how do we use that to get the enthalpy change? Well, we are going to use the following equation. Q equals mc delta T. Well, equation that most people call Q equals mcat, because the delta looks a lot like an A, and it's easier to remember Q equals mcat. But Q equals mc delta T is usually known as a calorimetry equation. It is the equation that allows us to convert from the temperature change to Q. Now, what is Q? Q is not delta H, and this is something that you need to make sure you understand. Q and delta H are different. Why? Q is simply a measurement of the amount of heat absorbed or released by the surroundings in joules. So Q is just heat. That's what Q is. It's heat. Q is not the enthalpy change. Why? Because if you remember, enthalpy change is per mole. Q is simply the amount of heat given off or absorbed by a specific reaction that we carry out in the lab in joules, not in joules per mole. On the other hand, on the other side, what are mc delta T? M is the mass of water, and this is where a lot of you are going to get confused. M is not the mass of the reactants, it is the mass of the surroundings of the water. A lot of the time, we know that the density of water at room temperature and pressure is 1 gram per cubic centimeter. Meaning that if we have 50 cubic centimeters of water, we have 50 grams of water. So cubic centimeters and grams, because the density of water is 1 gram per cubic centimeters and grams are interchangeable for water. So M is going to be the mass of water. Don't forget this, because a lot of the time you'll be adding reactants to that water, and it can be very tricky to remember that M is not the mass of something else. It's always of the water, the solvent that we're using. C is that specific heat that we just discussed. So the specific heat of water in this case, which is 4.18 joules per mole Kelvin or mole Celsius, depending on which one you're choosing to use. And then delta T is simply just the temperature change of the surroundings. So it's a temperature change in either degrees Celsius, if you're using degrees Celsius for the specific heat, or Kelvin if you're using Kelvin for the specific heat. Now, because this is a change in temperature, it is going to be the same whether it's joules or Kelvin. So let's look at the following things. I'm going to erase this here. So there are a few things that you need to consider or keep in mind while you're doing calorimetry. Oops. Let's go back to the Q is the amount of energy absorbed or released by the surrounding, not the system. This is very important to remember because it's very easy when you're doing calculations in calorimetry to flip a sign from negative to positive or positive to negative and then getting the answer wrong. Always make sure to double check the sign of Q, because depending on what they're asking you, your sign should make sense. If you have an exothermic reaction, then the system should be losing energy, negative Q, and the surroundings should be gaining energy, or positive Q. So just keep in mind, I like to put little subscripts in my work whenever I'm working with Q with MC delta T to remind me what is system and what surroundings. The density of water, like we said earlier, is 1 gram per cubic centimeter. So if we have 1 cubic centimeter of water, you have 1 gram of water. You have 50 cubic centimeters of water, you have 50 grams of water. A lot of the time, water will be given to you not in grams, but in cubic centimeters. So you should just remember it's a very simple and direct conversion. And then finally, the chemical in a solution have negligible volume. Whenever we're working with a solution and it has a specific chemical in it, that chemical has a negligible volume. So the volume of a solution in a reaction is essentially equal to the volume of the water. What do I mean by that? Well, let's say you have 50 cubic centimeters of hydrochloric acid solution, aqueous. Well, the HCl in that solution really has very limited volume. It has a very negligible volume. So when we say we have 50 cubic centimeters of HCl aqueous, we can take this to mean, for the sake of calorimetry, that we have 50 cubic centimeters of water. And because we have 50 cubic centimeters of water, we can also take that to mean that we have 50 grams of water, because that is the 1 gram per cubic centimeter density. If we have 25 cubic centimeters of sodium hydroxide solution, again, that's aqueous. Again, because the sodium hydroxide itself takes up very little volume, 25 cubic centimeters of aqueous sodium hydroxide, because aqueous means that it's in water, means that we essentially have 25 cubic centimeters of water. And therefore, 25 grams of water. And here's what the most important thing is. If I were to mix these two solutions, because in order for reactions to happen, solutions need to be mixed together. Then if I mix these two solutions, 50 cubic centimeters of HCl and 25 cubic centimeters of NaOH, that means in total, the volume of the mixture is 75 cubic centimeters of mixture that is aqueous. That means that in total, this reaction between these two is going to have 75 cubic centimeters of water. And that's very important to remember, because that is the number we're going to use here in M. And then 25 cubic centimeters of water means, 75 cubic centimeters of water means 75 grams of water. So this is a very important concept to understand. It's very simple and straightforward for the most part, if you just remember that anything that is aqueous is basically by volume all water. And that water has a 1 gram per cubic centimeter density, so we can convert cubic centimeters of water to grams of water directly. But keep in mind that if we're doing a reaction where we're mixing two solutions, then the volume and the total mass of water is going to be the combined volume, meaning we have to add them up. So now this is Q. This gives us Q, this equation gives us Q. Q equals MC delta T. What we get from this, however, is the heat given off or released by that specific reaction to the surroundings, not the enthalpy change. What's the difference? Again, heat, or Q, is in joules. It is the total amount of heat being given off or released. Whereas enthalpy change is per mole. So what you can think of this as, if we make a comparison to currency and to a paycheck, Q is your paycheck. Q is your total amount of money you're getting given at the end of the week or at the end of the 2 weeks by your job. Whereas enthalpy is your pay per hour. So enthalpy is in a standardized manner. It is per mole, like your hourly rate will be per hour, $15 an hour, $20 an hour. Enthalpy is 20 joules per mole, 50 joules per mole. Q, on the other hand, is just total. It's just joules. So again, your actual paycheck, just the dollars or the money. So how do we convert this Q to an actual enthalpy change, to per mole? Well, just like if you wanted to figure out how much you get paid per hour, you will grab your paycheck that you got and divide that by the number of hours that you worked, and that will give you your hourly rate. In order to figure out if you have Q, which is your total heat given off or absorbed, divided by the number of moles, that will give you your enthalpy change. Because enthalpy change is in joules, which is what Q is, per mole. Very important to look at units here, and the units will always help you out. So let's look at how we do that in the next slide. In order to calculate the enthalpy change from heat, we need to look at the moles of the reaction. So Q is the heat absorbed or released by the surroundings of a reaction, but it's not the actual enthalpy value for the reaction. In order to calculate the enthalpy value for the reaction, we need to consider two things. First is that the heat change for the system will be the same magnitude but the opposite sign of the heat change for the surroundings. What does that mean? That means if we have the system versus the surroundings, we'll put the surroundings in blue. The Q of the system is going to be the opposite sign as the Q for the surroundings. So the Q for the surroundings, I'll put here surroundings, and the Q of the system are going to have a relationship where they have the opposite sign. Q of the system is going to be equal to the negative Q for the surroundings. They're the same magnitude. So if the system absorbs 50 kilojoules, then the surrounding is going to lose 50 kilojoules. Why? Because those are the only two things present. The heat given off by the system is absorbed by the surroundings, and vice versa. The heat absorbed by the system is given off by the surroundings. If, let's say, the system has a negative 20 kilojoule Q, meaning that the system is releasing 20 kilojoules. Where those 220 kilojoules go, those 20 kilojoules are going to go to the surroundings. So the surroundings are going to absorb 20 kilojoules. So they have the exact same number but opposite signs. So that takes us to this first top part of the equation. Delta H, because delta H is of the system, we're never going to have the delta H of the surroundings because it's not a reaction. Delta H is always of the system. The delta H of the system is equal to negative Q of the surroundings, right? So why negative? Because the system and the surroundings are opposites of each other. If Q of the system is positive, then delta H is going to be negative, because if the system is absorbing energy, then the surroundings are absorbing energy, then delta H of the system is losing energy. If the surroundings are losing energy, then the system is absorbing it. And then the other part of this is that enthalpy is measured in kilojoules per mole. Because heat is measured in joules, we need to make heat dependent on the number of reactants or moles of reactants or products that are going on here. So in order for this delta H to be calculated, we need to divide the amount of heat energy given off by the surroundings or absorbed by the surroundings, or Q, negative Q of the surroundings, divided by the number of moles. So what does that leave us with? Delta H, which is the enthalpy of a reaction in kilojoules per mole, and that's going to be, again, always of the system, because delta H is of the system of the reactant. Q, which is negative heat energy of the surroundings in kilojoules, so Q is calculated in kilojoules, and we're going to do negative Q because that Q that we calculate in mcΔT is of the surroundings. And then divided that by the number of moles of the limiting reactant. So in the reaction, if there are two amounts, you will need to figure out which one the limiting reactant is, and that's the one that you use for your equation. If there's only one reactant amount given, then that's the one you're going to use. So this is what we use. So we're going to use a combination of the two equations. We're going to use Q equals mcΔT to find the Q of the surroundings. And then if we do negative that Q divided by the number of moles of the reactant, we can get the delta H of that reaction from that. So we're going to use a combination of both of these equations in order to calculate the enthalpy change of a reaction. So this is the whole process from practical all the way to the actual delta H for the theory. So if we look at this as a whole process, let's do this. The first step is calorimetry. And in calorimetry, we are going to measure delta H, or sorry, not delta H, delta T. We're going to measure delta T for the surroundings, as well as the mass of water. So we're measuring the mass of the water, we're measuring the delta T of the surroundings. From there, we can use Q equals, and this I'm going to put here, Q of the surroundings equals mc delta T to calculate Q of the surroundings. So from the calorimetry, we get the measure, I'm sorry, let me maybe make these not arrows. So from calorimetry, we're going to measure the delta T and the mass of the water. Then we're going to use the delta T and the mass of the water in Q equals mc delta T to calculate the Q of the surroundings. And then once we have the Q of the surroundings, we can use the delta H is equal to negative Q of the surroundings over N to calculate the delta H. So every step is needed. We need the calorimetry, actual practical, to measure the temperature change and the mass of the water. We're then going to multiply them together and times the specific heat of water to get Q of the surroundings. Once we have Q of the surroundings, we're going to grab that, the negative of that number, divided by the moles of the reactant, the limiting reactant, and that's going to give us the delta H for that reaction. Now, that N can come from a number of different places, from stoichiometry, it could be given to you, it could be calculated simply from being given the mass, and then you have to calculate the molar mass or divide by molar mass. So there's a few ways that you can get that n, and that's going where the critical thinking is going to come in, because you got to figure out where this n comes from. So let's look at some samples. This is an example from a paper too, a very old paper too. A student added 50.0 cubic centimeters of hydrochloric acid to 50.0 cubic centimeters of sodium hydroxide solution in a polystyrene cup. Polystyrene is just the chemical term or the chemical name for styrofoam. The temperature rose by 6.5 degrees Celsius. The initial concentration of each solution was 1.00 moles per cubic decimeter. Calculate the number of moles of acid used in the reaction. So a lot of the time, reactions or questions in the AICE exam will look like this, where they don't directly ask you for delta H. They're going to walk you step by step through the whole process. So here, they ask us to calculate the number of moles of acid used in the reaction. Well, why does this make sense? This makes sense because that last step that we just discussed requires us to divide by the number of moles of the reactant. Delta A, or HCl, is one of the reactants here. So more than likely what we're being asked for here is to calculate that N that we're going to use later on. So here we're being asked essentially, what is N equal to? So let's calculate the number of moles of acid. This should be a very simple and straightforward problem from chapter 3. We have a few different numbers here. So let's try to focus in on what we need. We're going to write them here on the side. We have that for HCl, the volume is equal to 50 cubic centimeters, 50.0 cubic centimeters. And the concentration, and we're actually going to put here, we'll put brackets for concentration. That way we don't get it confused with C later on. So the concentration is going to be, if we keep reading, the initial concentration of each solution was 1 mole per cubic decimeter. So we have 1.00 moles dm to a negative 3 as a concentration. For sodium hydroxide, NaOH, we have the same concentration and the same volume, because volume here says 50.0 cubic centimeters of sodium hydroxide of NaOH, and then we also have the same concentration of 1.00 moles per cubic decimeter. Now the other thing that they give us is the temperature change. They say that the temperature rose, and that's a very important word, by 6.5 degrees Celsius, meaning that delta T, the temperature change, is equal to positive, because it went up, rose, 6.5 degrees Celsius. Now you might say, Mr. Brenda, why are you writing a positive there, right? We don't need that. We know it's a positive number. It is always useful when you're doing thermodynamics, when we're doing these kind of calculations with energy, to put the sign, even if it's positive, put the sign in front of the number, because it will allow you to keep up with what you're looking for. It will allow you to keep up with the signs, whether it's positive or negative. It will remind you whether signs are positive or negative, because that's something we need to constantly think about in thermodynamics. So here they're asking us how many moles of acid are used. So we're not focused on the HCl. Number of moles of acid, the N of the acid, is going to be, from looking at this, we have the volume and the cubic decimeters. So we have 50 cubic centimeters, which is this equivalent of 0.0500 cubic decimeters. And since the concentration is 1 mole, 1.00 moles per cubic decimeter, all we have to do is multiply these two numbers, because again, the signs will always help you. The signs cancel out if we do that. And so we have 0.05 times 1 gives us 0.0500 moles of HCl. That's our first step. Notice, we're not asked to use the delta T. We're not looking at sodium hydroxide, because right now what we care about is what part B is asking us for, which is the number of moles of the acid. They guide you through the process. Trust the questions to guide you through the process, because this is going to be a number that we are going to use later when we calculate delta H. So if we look at the mark scheme here, very simple, straightforward. 50 times 1 divided by 1,000. The 50 divided by 1,000 is what gives you those cubic decimeter conversion from cubic centimeters. And then the times 1 is because the concentration was 1 mole per cubic decimeter. So 5 times 10 to the negative 2, or 0.0500 moles of HCl. So we can add that to our list here. We can put here that the number of moles, N, is 0.0500 moles for hydrochloric acid. Let's look at the next part of the question. So I'm going to erase some things here. I'm going to erase this, but I'm going to keep our numbers there on the side. So let's look at the next part of the question. Ooh, I wish I could move that. So here, I'm going to get rid of this for a second. Here we have a student added 50 cubic centimeters of hydrochloric acid, 250 cubic centimeters of sodium hydroxide solution. Temperature went up by 6.5. So it's the same heading because it's all part of the same question. But this is part C. Before we did part B, which is where we found the number of moles of hydrochloric acid. Now we're looking at part C. Part C now says calculate the heat energy evolved in the reaction. Assume that the final solution has a specific heat of 4.18 joules per gram Kelvin. So they're giving you Z, and a density of 1.00 grams per cubic centimeter. So here we're given a bit of more information, and the wording is very important here. So if we look at our wording, please ignore this for a second, it says calculate the heat energy, not the enthalpy change, the heat energy. Meaning that what we're looking for here is Q. So remember, heat energy is Q, enthalpy change is delta H. Evolved from this reaction. Now, the word evolved is also very telling. Why? Let me use a different color, actually. The word evolve is telling because evolve means it's released, not absorbed. If it's absorbed, it will be absorbed. But evolve means release, meaning that we know that the reaction is releasing energy, which checks out with what we already know. Always, always, always think about the actual theory behind thermodynamics when you're doing these math problems. Don't just get stuck on the math, because the theory can double check your units. Evolved means that the reaction is exothermic, meaning that checks out because the temperature of the water went up. It rose by 6.5 degrees. So what does that mean? That means that Q of the system is going to be, Q of the surroundings is going to be positive because the system is releasing energy, and that energy is being absorbed by the surroundings. It also means that delta H at the end is going to be negative because the system is releasing energy. So we can put that here as an aside. Delta H at the end should be negative because it's an exothermic process. The energy is evolved, temperature goes up. And the Q of the surroundings, which I'm going to put here in yellow, should be positive. So we'll keep that in mind when we're doing our work. Now, what we're being asked for here is what is Q, right? So what is this Q here in yellow? So let's look at that. Now, how do we calculate Q? To calculate Q, we need to remember our equation. The equation to calculate Q is of the surroundings, so we'll put that here just to make sure, is equal to mc delta T. And remember, M is always of water, of the solvent, right? So how do we calculate Q of the surroundings? First of all, we need to know what M is. Well, M can be a little tricky. Why? Nowhere here does it mention water. But what it does mention is the two solutions. And remember, solutions by volume are mostly going to be water volume. So when we look at these two solutions and we have 50 cubic centimeters, so the volume, oops, let me do this in pink. The volume of the H2O is 50 cubic centimeters. Oh no, not the H2O, sorry, the HCl is 50 cubic centimeters. And the volume of the NaOH is 50 cubic centimeters. Then what is the mass of water? Where does the mass of water come from? Well, if we remember what we talked about earlier, the volume of HCl and NaOH are going to be mixed together. And it says so in the equation. If I look at my question, sorry. If I look at the question, a student added 50 cubic centimeters of hydrochloric acid to 50 cubic centimeters of sodium hydroxide. Those two 50 cubic centimeters are added together. So the 50 cubic centimeters of hydrochloric acid are added to the 50 cubic centimeters of sodium hydroxide, which means the volume of the overall solution or mixture, we'll put mixed solution here, is 100 cubic centimeters. 50 plus 50. Well, how does that relate to mass of water? Well, remember, the volume of the mixture is 100 cubic centimeters. Because these are aqueous solutions, the volume of the water is 100 cubic centimeters. Because these are aqueous solutions, and they're mostly water. The volume of the actual chemicals in them are negligible. So that means we have 100 cubic centimeters of H2O. Well, but we don't need cubic centimeters, we need mass. Well, that's why, again, if we look at our question, the question says the density of the solutions, which is essentially the density of water, is 1.00 grams per cubic centimeter. Meaning those 100 cubic centimeters of water can be translated to the mass of water, which is 100 grams. It's a 1-to-1 ratio because 1.00 grams per cubic centimeter is the density of the solutions and therefore the density of water. So that means, what is M here? M is 100 grams of water. C is a little easier, right? Because C just comes from our work. What is C? C is simply just the specific heat of water, which is 4.18 joules per gram degrees Celsius. And we know that because we should memorize it, but also the actual question says it. Assume that the final solution has a specific heat capacity of 4.18 joules per gram Kelvin. And you can always assume that because that's the specific heat of water, which if these solutions are mostly water, should be the specific heat of the solution. If the question says that the specific heat of the solution is something else, then you should use that other number, not 4.18. But unless it otherwise says it in the question, then you're going to use 4.18 as your C. And then finally, we have delta T, which comes directly from the question. The question said that the temperature rose by 6.5 degrees Celsius, meaning that the temperature change, delta T, is 6.5 degrees Celsius. So all we have to do now is actually grab these numbers and multiply them by each other. The hard part is not the actual math, it's just figuring out what all the numbers are. So here, Q of the surroundings, which I should probably put in yellow. I'm going to put that in yellow. Q of the surroundings is going to be equal to positive, because of that positive 6.5, everything's going to be positive. So 6.5 times 4.18 times 100 is going to give us positive 2717. And what is the unit here? Well, look at the units that we have in our work. Grams cancel out, Celsius cancel out, and so the only unit we have left is in joules. So what is Q of the surrounding? Q of the surroundings is 27. Oops, let me erase the question sign here. the Q of the surroundings is going to be positive 2717 joules. And that's a number we're going to use later. Notice how I keep using the numbers from that heading, right? So if we go back now, and this is our math. This is the work that you should be showing. This is just me keeping track of everything. So if we go back to our question then, turn this off, and let's erase some of this. If we go back to our question, what is the specific heat of, what is the heat energy involved in the reaction? Then the answer to that is just going to be the Q of the surroundings, essentially. Oops, let me make that a different color. Q of the surroundings, which is going to be equal to positive 2717 joules. And if we look at our answer key, that's what we have. Heat energy involved equals MC delta T, or MS, don't worry about this, that's another way of doing it that we're not going to go into. Or you could describe what you're doing. So what essentially this is saying is that you get 1 point for the equation or the description of the work, and then 1 point for the actual answer, which is 2717. They'll allow anywhere from 2700 to 2717 because of rounding error, because you could have used 4.2 instead of 4.18. But you should have gotten the proper answer. So that's Q. Q is 2717 joules. The last thing we're going to end up doing is that we need to find the enthalpy change. So guess what? If that was B, was N, finding N, and C is finding Q, then what do you think D is going to be? D is, again, same prompt, same heading here. Calculate the molar enthalpy change, or just enthalpy change, just the full name of it, for the reaction. Molar enthalpy change, again, the word molar just means because it's per mole. Enthalpy change is really what tells you what we're looking for. Because this is the enthalpy change, what we're essentially being asked to do is to find delta H. So we're going to use all of those numbers that we just gathered to say, okay, what is delta H? So let's look at that number. So what is delta H going to be? Delta H, I missed a few things here. Delta H, if you remember, delta H is going to be equal to negative Q of the system. Sorry, of the surroundings. Because delta H is for the system. Delta H of the surroundings divided by N. Well, we already have these numbers. Because from part B, we found out that the number of moles of hydrochloric acid is 0.0500 moles. Now, we weren't given the numbers for sodium hydroxide. And we could do the math to figure out which one the limiting reagent is. But if you do that, you'll notice and you'll find out that they are actually the same number of moles, and it's a 1-to-1 ratio in the reaction. So it doesn't actually matter which one you use. But since part B asked us to find the number of moles of hydrochloric acid, that is a clear indication that this is the number we should use for it. And then in part C, we found the Q of the surroundings, 2717 joules. So all we have to do to find delta H is negative Q of the surroundings, so negative 2717, divided by N, which we found in part B was 0.05 moles. Let the question guide you. Notice we had already found what we need. When you get lost, look at the prior parts of that question, because a lot of the time they'll help you figure out what you need to do. So if we do negative 2717 divided by 0.05 moles, the answer we get here is negative 54,340. And again, we look at our units. Q was in joules, moles in moles, so this is in joules per mole. Or if we want to put it in the way that Cambridge usually puts it, joules moles to the negative 1. So, or depending on what unit they ask us for, this could be negative, if we divide by 1,000, 54.3 kilojoules per mole to the negative 1. So we can divide by 1,000 to make it kilojoules. It gives a much cleaner and simple number. So I'm going to write that here. I'm going to write it in black, but you'll see it when I switch over to the other screen. Delta H is going to be negative 54.3 kilojoules mole, negative. Oops. Oh, let me write it in red, actually. That was a bad color for me to choose. So in red, 54.3 kilojoules mole to the negative 1. Or negative 54,340 joules mole to the negative 1. So why am I writing in both ways? Because we didn't look at what the question was asking us for. Very simple equation, right? All we need to do is follow the steps that they're outlining for us. So how are we going to answer this? Well, notice that this question, I'm going to erase this part right here. Notice that this question does not ask for a specific unit. It says calculate the molar enthalpy change for the reaction. It doesn't say in joules, in kilojoules. So all you have to do here is show your math of delta H is equal to negative Q of the surroundings over N, meaning negative 2717 joules per 0.05 moles, which is equal to 54,000 negative 340 joules mole to the negative 1, or we can put our answer as negative 54.3 kilojoules mole to the negative 1. Either way, you'll get the right answer because the question is not asking for a specific unit. If it was asking for either joules or kilojoules, you will need to put in the proper unit. But because they're not asking for a specific unit, we can get away with either or, as long as we have our unit on the number. So if we look at the mark scheme here, the molar enthalpy change being negative 2717 divided by 5 times 10 to a negative 2, which is 0.05, is the first point, so the work is the first point, and then your final answer with the appropriate units is the second part of your point. So allow consecutive consequence to answer in B and C, meaning that you do get error carried forward. So let's say that you had gotten the wrong number for B or the wrong number for C. As long as you do this calculation right, you will get the right or the points for it being the right answer. So you need to make sure that you look at that when you're doing your work. And don't get discouraged. If you don't know how to do part B or you don't know how to do part C, then just put a number down and then use it for part D so that you can get some points. And that's very important what error carry forward. Just because you don't know how to do part B or part C, if you know how to do part D, then just put a number for part B or C and then just use it here so that you can get error carry forward. All right. So that's this part. So you notice that this is 3 questions, but in reality, it's actually just the steps to one much larger question. And these are very common questions for calorimetry. Now let's look at another type of calorimetry called spirit burner calorimetry. Spirit burner calorimetry, like all calorimetries, it addresses the same topic. It addresses the topic of the amount of energy needed for a reaction to happen, either amount of energy given off or amount of energy absorbed. It calculates Q, so on and so forth. Now, while calorimetries work perfectly for aqueous reactions or for reactions that dissolve something in water, any reaction that is extreme heat, like a combustion reaction, would not work with a spirit burner calorimeter because that styrofoam will melt under extreme heat. So, for example, if we wanted to look at the amount of energy given off by burning methane or by burning ethanol, we wouldn't be able to use the calorimetry we just discussed. So what we will do in that scenario is that we will use a spirit burner calorimeter. Spirit burner calorimeters are used to measure essentially any combustion enthalpy change. So enthalpy changes of combustion are measured using this setup. The setup is actually pretty simple. We have a heat shield. So what we have out here is usually some kind of cone or some kind of cylinder, which is made out of something that resists heat. And then we have a spirit burner at the bottom. Spirit burners are just essentially like tiki torches that you will use in your backyard. It's a little glass container that has a wick, and in that wick you put the thing that you're burning. In most cases, usually an alcohol or alkane, and then we can light that spirit burner. So what happens is that as this burner burns, the liquid that's in there, so the liquid, whatever liquid this is going to go up the wick, and that's what gets burned by the spirit burner. So this is a combustion reaction. It's a combustion reaction because the whatever liquid we have, ethanol, propane, whatever liquid we have here is being reacted with oxygen in the air, create a combustion reaction. So the Q that we're finding here is for a combustion reaction. But we can put a flame underwater, right? So how do we translate the heat given off by this combustion reaction to the heat of water exchange or water temperature going up? Well, we are going to use a metal calorimeter, which is essentially just a beaker made out of copper with water in it. And we're going to measure the temperature of that water. Essentially what is happening here is pretty straightforward. We're essentially boiling the water or heating up the water using this fuel. So the heat given off by this flame, by the combustion reaction, because of the shield, has nowhere to go but to the calorimeter, the metal calorimeter. And so that goes to raising the temperature of the water. And we can directly measure the amount of heat given off by this reaction because it's going to directly go to just raising the temperature of the water thanks to this heat shield. From there, it's the same calculations that we thought about before. The difference here is going to be that the specific heat is going to be slightly different because the specific heat for a spirit burner calorimeter can vary. Most of the time, however, that specific heat is going to be given to you by a question. And that specific heat is a lot of the time, for the sake of simplicity, the same as that of water. So let's look at a question here. Again, the setup is different, but the idea is the same. We're looking at some reaction. That reaction is, in this case, because combustion is giving off heat. We can measure how much heat is given off because it's going directly to raise the temperature of the water. So with the delta T and the mass of the water in here, we can figure out Q. And then by measuring how much of this fluid that we burned, the mass, we can calculate the moles and therefore get the enthalpy change. So let's look at a question like that. This question is from a paper 2. Notice, slightly different picture, but it's the same setup. A value for the enthalpy change of combustion of alcohol, C3H7OH, so this is propanol, was determined in the laboratory using the apparatus shown below. The apparatus shown below is essentially a spirit burner calorimeter. The following results were obtained. So they tell us we have the mass of the water in the calorimeter was 200 grams. So they tell us the mass of the water. The initial temperature of the water was 15 degrees Celsius, and the final temperature was 30 degrees Celsius. So they don't give us delta T, but we can calculate delta T from these numbers. And then the mass of the alcohol burned was 0.9 grams. Calculate the heat energy required to raise the temperature of the water from 15 degrees Celsius to 30 degrees Celsius. So here we're not looking for delta H, we're just simply looking for Q. Again, how do we know that? We know we're looking for Q because this is telling us heat energy required. Heat energy being Q, not delta H. Delta H is either enthalpy change or molar enthalpy change. And so we need to show our calculations here. So let's write down all the numbers that we're going to need before we go to another screen. So what numbers are given to us? What numbers do we need? Here we have, first of all, the mass of the water. They tell us that the mass of the water, so no thinking here, they tell us mass, not even volume, is 200 grams. Then they tell us the initial temperature, and we're using green. The initial temperature of the water is 15 degrees Celsius, and the final temperature of the water, TF, is 30 degrees Celsius. So they don't give us delta T, but we can calculate delta T from those two numbers. Because delta T is simply going to be the final temperature minus the initial temperature. Meaning that for this, delta T is going to be 30 degrees Celsius minus 15 degrees Celsius, which is 15 degrees Celsius. So the change, very simple, 15 to 30, the change there being 15 positive. Remember, we always want to put a sign in front of those delta T's. And then they tell us the mass of the alcohol, which we'll do here in pink. The mass of C3, I'm going to put C3H7OH, because this is going to be important later, is 0.90 grams. Apart from that, they tell us that the heat capacity for this calorimeter, so C, is going to be 4.2 joules per gram Kelvin. Remember, we calculated that delta T is positive 15 degrees Celsius. This can also be positive 15 Kelvin, because a change in Celsius is equal to a change in Kelvin. So I'm going to put here positive 15 Kelvin. Why? Because I can already see that my C is in grams times Kelvin. So that's going to make it a little easier. So finally, what am I looking for here? I'm looking for Q. And it's calculate the heat energy required to raise the temperature, right? So this is already, we're not going to be worrying too much about the sign, because they're just asking us for a number, not a sign. Calculate the heat energy required to raise the temperature of the water. We know Q is going to be positive because it's heat energy required, meaning that it's being absorbed. So we're not going to worry too much about the sign there. So again, how do we calculate this? The actual equation is exactly the same as what we saw before. Q is equal to mc delta T. So what is Q? Q is the Q of the surroundings, so we'll be looking at the Q of the water. M is the mass of the water, which they were nice enough to give us, not even in volume. They just told us it's 200 grams. C is the specific heat of this particular calorimeter, which is 4.2 joules mole Kelvin. And then delta T we calculated is TF minus TI, which is 30 minus 15 is 15 positive. And we're going to put Kelvin. Again, we could put degrees Celsius. The number doesn't actually change whether we put Kelvin or degrees Celsius. The reason why we're putting Kelvin is that, and actually let me do this in the soft red. The reason we're doing Kelvin is that it matches the units that we're using for the calorimeter. So here we can see that the grams cancel. Oops. Is that moles? Or I think I put the wrong thing here. Grams, not moles. I put, this is the wrong thing. So this should be grams, not moles. My bad there. So the grams cancel, and this is why it's important to put your units, so you can catch mistakes like that. The grams cancel, the kelvins cancel, and we end up with Q being 200 times 4.2 times 15 positive. That's going to give us 12,600 joules, because that's the only unit that's left, as Q. Or, if we wanted that in kilojoules, we'll say 12.6 kilojoules. Again, that's going to depend on whether the question asks us for a specific unit or not, and if they don't, we need to make sure we put the unit on that answer. So this either Q is going to either be 12,600 joules or 12.6 kilojoules. So that's my work. It's just the same equation, Q equals MC delta T. The fact that this was a spare burner does not actually change the math. At most, it might change this number, but it actually just makes it a little easier because the mass of the water is separate from the solution, so it's more straightforward. So if we look at this, we go back to our problem here, we can see that enthalpy is going to be equal to 200 times 4.2 times 15, which is what we had, or 12.6 kilojoules. So you have 1 point for the work, 1 point for the answer. So I'm going to erase this because we're going to use it in the next problem. So that's our Q. Now they're not asking us for delta H, they're only asking us for Q because this is part CI. So imagine, what is part CII? Part CII is either going to be delta H, or more importantly or more logically, what we need to find delta H. We have Q already. So what else do we need to find delta H? N. And part 2 is going to be exactly that. Calculate the number of moles of the alcohol burnt. We have the mass of the alcohol. We need the number of moles. This is a very simple and straightforward problem. All we need to do is find the molar mass of this compound. Well, if this is C3H7OH, carbon has a molar mass of 12, hydrogen has a molar mass of 1, and oxygen has a molar mass of 16. There are 3 carbons, 7 hydrogens here, and 1 hydrogen here, and there's 1 oxygen. That means we have 7 times 12 is 36, plus 7 times 1, plus 16 times 1 is 16, plus 1. 36 plus 7 is, actually, let me just do the whole thing. 36 plus 7 plus 1 plus 16 is going to be 60 grams per mole. So the molar mass of this compound is 60 grams per mole. If we have 0.90 grams, and we multiply that by 60 grams per mole, or sorry, not multiply, we divide that by 60 grams per mole, in order to get the number of moles, 0.9 divided by 60 is going to give us the number of moles, which is 0.015 moles of the alcohol. So the N here, and let me actually use a different, actually no, I'll use the same, pink, is 0.015 moles of C3H7OH. Now, this is a very simple, straightforward problem, right? This is more a chapter 3 problem, but in order to do part 3, we're going to need that number of moles. And ignore this 12.6. This 12.6 is actually part of the prior mark scheme, the 12.6 that we have here. This top part is really what we need. This should say not 12.16, but 0.015 moles. I'm not sure why that's like that. So that is the number of moles. So all we have left to do after that, now that we have the number of moles, is going to be to part III, or part 3, which is going to ask us for the value of the enthalpy change of combustion. Now, this is where the definitions that we did come in handy and are important. Remember that the enthalpy change of combustion is based on a very specific number of moles, and that is the number of moles of the fuel, of the thing that we're burning. So that's why when we do our equation here, and we'll do it here on the side, remember that in order to find our answer here, we're going to use the equation that delta H is equal to negative Q of the surroundings over N. What is this N of? Because we're doing enthalpy change of combustion, this is N of the fuel, of the thing that we're burning. Not of the oxygen, not of the water being created, but of the thing that we're burning. So we have the numbers already. Q, negative Q is going to be negative 12.6 kilojoules. And again, this is all, it walks you through it. Part I, we found Q. Part II, we found the number of moles. So part III, all we're doing is putting those two things together. Negative 12.6 divided by 0.015 moles. So 12.6 divided by 0.015 gives us 840 kilojoules per mole. And that is going to be negative. And think about it. Does this make sense? Logically, theoretically, does it make sense? Well, it's a combustion reaction. So our negative number definitely makes sense. Because that's what it tells us it's exothermic, which all combustion reactions are. The number is really large, 840 kilojoules. Does that make sense? Well, yeah, it's a combustion reaction. Combustion reactions give off a lot of heat. So this number makes sense logically for our answer. Calculate the value of enthalpy change of combustion of 1 mole of alcohol. Then the answer is going to be simply just negative 840. Again, if you couldn't do one of these two parts, if you forgot how to do Q, if you forgot how to do the number of moles, simply put a number there so that you can use it in this equation, and you will get error carried forward for this problem. That's it. I mean, there's a lot of different math problems that you can get with calorimetry, but this is the essence of them. Using calorimetry to find the temperature change and the mass of the water, in order to then find the Q of the reaction, and then the number of moles of the reaction with the Q will give you the delta H. That's the essence of all calorimetry, with slight variations here and there that you have to account for. But that is it. That is everything for section 3 of chapter 3 or 6. I will see you all in the next video.